current slide. I'll even turn on, I'll turn on the projector already. All right, not many new announcements. Nothing new. Nothing on the administrative calendar for this week. And the volleyball team this coming weekend, the first Friday, Saturday, Sunday, will be the NJCAA District LM Tournament. I don't know what all these initials stand for.
Junior college.
Yeah, I'm guessing National Junior College Athletic Association District L/M Tournament. I don't know what L/M is. Maybe that's
somebody.
Huh?
Lawson and somebody.
Well, it could be, or it could be that certain states are in certain divisions, like they start with A and go through Z or something, and we're in LM. I don't know. But it's going to be held up in Boaz, Alabama, Friday, Saturday, and Sunday. So if you happen to be up that way and want to stop in and cheer the team to victory. What is the college up there? Is that Northwest Shoals? No. Yeah.
Alabama?
Yeah, near Boaz.
Was that the old spot in the state system now? Was that the old Florida State Teachers College?
Could have been. Okay, I don't know. Don't know for sure. But anyway, that's where it is. Maybe Calhoun has a campus at Boaz. I don't know. Don't know for sure. And then I think I've announced this one before. There's a postgraduate student, a postdoc student at UAB. She's one of the newest cohort of merit scholars at UAB, whatever that means. She came across a one-week summer opportunity for college students interested in biopharma manufacturing careers, thought that maybe one of our students might be interested. The students are paid $1,000 for that week, and travel expenses are covered. The application deadline is sometime in January, and I'll share with you on this piece of paper all the information I have, which that's about it. There's a website link that you can go to and find out more. Okay, that's about it. No one else has come in. My mark and my memory are that we are on we're in Chapter 13, Functions of Several Variables, 13.6, Directional Derivatives and Gradients. We had done quite a bit with directional derivatives just last time, started on the gradient part, and we're on example 4 on page 923. Any questions before we get started?
Yeah, but it's not going to help you right now.
Okay. Well, I don't mind answering it, or trying to. Or you rather wait till a more opportune time?
Yeah, I just have to go back and just reread that.
I couldn't hear, sorry.
I said I just got to go back and reread
Oh,
that.
okay. All right, well, here is example 4. Find the directional derivative of f of x is equal to 3x squared minus 2y squared at the point negative 3/4 0 in the direction from p, which is negative 3/4 0, to q, which is 0, 1. Ooh, okay. So it seems like we're going, okay. The title of this is Using the Gradient to Find the Directional Derivative. And that comes from the last thing we did, so let me back up one. Here was theorem 1310. You see the directional derivative in the direction of some vector u, and that's supposed to be a unit vector u, would be it of a function f of xy would be the gradient of f of xy dotted with that unit vector u. So that gives us sort of a cheap and easy way to do a directional derivative, perhaps a little easier than what we've done before. So we got two things to do in my mind here. Well, number one, I'm a cynic, okay? I want to make sure before I launch into trying to solve a problem, the problem makes sense. So the question is, for my viewpoint, is this point actually on that function? Now, I'm hoping they got it right, and I bet they did, but I like to always check this. Which you put a negative 3/4 in for x, that would be 3 times a positive 9/16 minus 0. What does that come out being? Whoops. Well, wait a minute. I don't guess it matters. So this thing doesn't give us a value for it, so no, it really doesn't matter. 27/16, but it doesn't. That doesn't matter. That would just give you the value for z, and we don't know anything about z. Sorry about that. That was of no consequence. None whatsoever. Thought it was, but it isn't. Okay, so at that point. In the direction from that point to Q1. So two things we've got to do. What are they? Okay, to get our gradient of f. That's exactly how we do that. So the gradient of f, which is, by the way, a vector, okay, would be what? 6x in the I direction, right? Second?
That's just a constant, it's 0.
Yeah, okay, yeah. For the x part, yeah, for the I part, yes. I could have done plus or minus 0 there. I didn't because, yeah. Yeah. Minus 4y in the j direction. So there's our gradient of f. And what was the other thing we needed? From P to Q. So let's determine what vector that is. P to Q would be what? Mm-hmm. So that would be minus 3/4 I. Yeah, that's what I heard. Okay. Plus, yeah, plus J. Right? Now, that gives us the vector in whose direction we want to go, but what we need is not just any old vector in that direction. We need the unit vector. So we need to determine this vector's unit vector, which would be, whoops, right, it would be that vector over its magnitude. Okay, so the unit vector in the direction of PQ, I'm going to put it like that so I know what I'm talking, well, sort of know what I'm talking about. That would be minus 3/4 I plus J.
Oh, that's right. 3/4. Okay, that's over 9/16 plus 16/16. That's 25.
Yep.
And then the unit vector.
So this is square root of 25/16 is 5/4.
3/5.
Right. That would be, the unit vector would be minus 3/5 I
Plus 4/5.
4/5 J. And then a very quick check that it indeed is a unit vector, because this square would be 9/25 plus 16/25 is 25. So, we've got our two pieces there. What is your directional derivative in direction of this vector u of this function 3x squared minus 2y squared? It's the,
Now, if we take that as
yeah, and do the dot product of those two vectors. And this will be a number. What's that? Okay. There's your... Right.
Well, we know what the unit vector is.
Right.
Go back and get the fxy.
Yeah.
6x.
Yeah. Well, yeah, okay.
6xi.
What?
Minus 4yj.
Right.
The unit vector 3.
Okay.
This I.
Yeah.
4 plus j.
Yeah. One thing that we probably should do first is evaluate this del at that point, negative 3/4 0. So this would be del f at minus 3/4 0. And that would be, yo! Well, let's first evaluate this at that point, so we know what gradient vector we're dealing with. See, this has x and y's in it. That's where we get our x and y. Okay, so that would then be minus 3/4 of x. That would be 2 will go into that 3/2. Ooh, I messed that up. Minus 9/2, isn't it? Yeah. Minus 9/2 I. And 0 on j because put a 0 in there. I hope that's right. Minus 3/4 times 6, 4, that would be 3/2, and minus 3/4. All right.
That's the unit vector.
I got 27 tenths. Did you or?
Yeah, you got the x component over here times the unit vector x component.
Yeah.
Multiplying.
This times that. Yeah. That would be a positive 27 over 10. And then this is a 0 times that.
Negative from negative to where I get that from.
And then the y component is there.
Positive from.
What's that?
Where did you get the positive from?
I
said, where did you get
positive,
the positive?
okay. This was a minus here because it's a minus times a plus. It's a minus here.
Okay.
And then this was a 0. And then minus here and a minus here. Minus times minus plus.
Okay, okay. Yeah. Screw it, I need to get the minus sign down here for the unit vector. Okay.
Shouldn't have been crowding things so much. I thought there were going to be more calculations than this, but there really weren't. Should have spread that on out a little bit.
if they give us a vector or
Right.
just follow these steps, we got to get the unit vector, okay, P to the Q over
Right.
PQ, and that's going to give us the magnitude of the unit vector right there.
Right.
And then, okay, P to Q got to be 3/4 IJ. Okay, there. That's over the magnitude. And then do the multiplication. Okay, then we got the gradient of the so-called del
Right.
f of x, partial of f of x,
Right.
the partial f of y times the unit vector dot.
Right. Dotted with that.
I
Yeah.
thought once we dotted it, we automatically get a scalar.
Yeah, and you do get a scalar.
That's a
Derivatives
scalar.
are scalars. Yeah. Derivatives are scalar. It's derivative. It's not. It's a derivative of a scalar function, which then will have to be a scalar number. It's just in a direction. It's how that function is changing in that direction. So that will be a scalar value. It seems like to me somehow it ought to be a vector also, because you take derivative of a vector, you get a vector, but you're not. You're taking derivative of a scalar function. And so you get a scalar number. Yeah. Oh, wait. They got a minus, so I did something wrong. Wait a minute. You were probably right. You know, it helps to write the problem correctly, doesn't it? No, I did it backwards here. I think you were saying it right and I was doing it wrong. It's from P to Q, so it's Q minus P. So that would be a plus there. Yeah, and this would have been a minus here. The minus didn't hurt me because it wasn't going to contribute anything. But yeah, this should be the plus here and the minus there. Sorry about that.
Just go in opposite direction.
Yeah, exactly. So this is a minus 5/4. No. No,
Minus 2/4.
yeah. Okay, no, it's 0 minus a minus, which is positive 3/4, and 1 minus 0. I did the second part right. I didn't do the first part right. Okay, sorry. So that's a positive 3/5 plus 4/5 j. So, and so then when you do that, so your question was very valid. Where did I get the plus sign? I made it up. Okay, I just was really sloppy. It is a minus 27/10 because from P to Q, meaning this minus that, which is a positive 3/4 side, this minus that is a positive j. So I got the positive there right, but I got this one wrong. And then when you divide by the magnitude, which is 5/4, then this becomes 3/5 I, and this becomes 4/5 j. So we got that right, but that should have been a positive here, not a minus. So then when you plugged in here, that gave you a minus 9/2 I, minus 9/2 times. Excuse me, I've got the hiccups. 3/5. The dot product there, that gave you minus 27/10. I leave that sign right there. I did this minus this and this minus that. I don't know where that came from. So that is a negative. Sorry about that. Now, this could have all been made obviously clear if we had drawn what this function is. And what is that? If this indeed is your z, get my pen back. If this is your z, what kind of shape is that? Yeah, yes, exactly. Right.
It's the parabola going this way.
Yeah, it's a hyperbolic because this is a hyperbola here, and then either one of those would be a parabola. This parabola, when x is 0, your parabola is going down in y and z, and when y is 0, your parabola is going up and on the xz plane. So yeah, that's your hyperbolic paraboloid. And I think they'll show the picture, which I'm glad I don't have to draw. Because the partials of f are continuous. I guess we should have said that, okay, but we just looked at it and saw they were. It is differentiable, and you can apply the theorem. A vector in the specified direction, if I had written it carefully, I would have seen this. 0 minus a minus 3/4, which is 0 plus 3/4 I, 1 minus j. So 3/4, that's where I blew it. I plus j, then divide by its magnitude, and you get 3/5 I plus 4/5 j, which is what we got after I made the correction of the minus I. And then the del f, or the gradient of f, is the partial of f with respect to xy, with respect to xi plus the partial of f with respect to yj, 6x minus 4yj, the gradient at that point. I should have done this like they did, a bit more orderly, done that evaluation before we started doing the cross product. So that evaluation was negative 9/2 I plus 0j, because put a 0 in for the y and you get 0j. Now, dot those two, this dotted with that, this dotted with that, that gives you your minus 27/10 and plus 0. They write it out for you here, and that is minus 27%. So here's the drawing of it. Okay, and again, now we don't have the thing on. Oh, there it is. Okay, here it is. You got hyperbole here and here, this way and that way down here, going opposite directions, depending on which axis you go out. When y is equal to 0, that's in the xz plane, you see that is a parabola going upward. And when you do x equals 0, so looking at it this way, you've got the parabola going downward. Here, it would be at x equals 0. You've got slightly going down like that. So, sure. Yeah.
Now, when we have 0, 0, 0,
Yeah.
right at that, right, that's 0,
Yeah.
0, 0.
It's
Now, that's
0,
the
0,
south.
0, exactly. That's
Or
the
the
south.
south.
That is the bottom of the south, right? And it's going up from there, down in this direction from there, and then the rest of it.
Okay, you see that point P to Q?
What's that?
P to Q.
Okay, yeah. Okay, here is point P was the negative 3/4 0. So negative 3/4 on x, here is 1, there would be minus 1, there's negative 3/4 0, and then Q is 1, 0 here. So there's your vector, and the unit vector along there was this value. Because that is a plus, the difference between these two is plus 3/4 took this and moved it to the origin, it would be plus 3/4 x. Where was it? I guess it was on the previous slide. When we did the subtraction. There, okay. 3/4 I plus 1j. And that's what we saw here. Moving 3/4 of the way in the I direction, there's half 3/4, and then 1 in the j direction, which would be here, so that's why this would have translated to there. Okay. But it's at that point here, so you raise this up, and then its gradient is.
That's from that point P going up.
That's the
zeta point.
Yeah, this is the, if you plug in negative 3/4 here and 0 there, that gives you your minus 9/2. No, you square it. That would give you negative. That is the thing we did at the very beginning, which I said wasn't important, but it is now. That would be a minus 9/16 times 3 would be minus 27/16. So that would be here. 27/16 is 1 in 11/16. Yeah, 1 in 11/16. That's your z value here. Your y value. That's for 0. Okay. Yeah. And so the slope here, the derivative here at that point on this function is going down like this, so that's why you get a negative 2 7/10 slope there in this direction. Has to be in that direction. So it's pretty steep, almost -3. These graphs, I couldn't even begin to draw them myself and then get anything that made sense out of this. It sort of does here, but it's a stretch. Because I can't really tell which surface I'm on here. Looking at this, I would have thought that your saddle was like this here, and you were continuing that up here, but it looks like you're on the back side of it, you know, and I guess you're not. Yeah, because these are hyperbole opening up like that, so the shadowing or shading on it is not particularly helpful to me. I guess what this shows is that you have something on the back side of this. This is the side on the negative y direction. This is the side on the positive y direction, and this is on the positive y direction, coming down this way. But
okay, on that whole saddle, now you take the saddle.
right.
It's coming down like this. This saddle is making it wrap around this way. Is it doing that at the same time?
Down here at the bottom.
Well, all the way up.
Okay. Okay. This is hyperbola up here. Yeah. If your z equal any fixed number, that's going to be a hyperbola. They're opening this way, coming up, and opening on the y-axis going down, opening on the x-axis coming up. Hyperbola, you know, opening outward. So they're doing like this here and like this down here.
Yeah, but I'm saying if you sit in it, something.
Yeah, I'll sit here.
Yeah, well, we'd be holding at the top.
Yeah, and holding here, and your legs will be going over the y,
the
y-axis. Yeah, and that, and in x equal constant planes, these are all parabola doing like this, and the y equal constant plane like this, they would be parabola opening like this, but they're, because this is moving out here, this one's here, and the next one's deeper on both sides, you know, going down like that, but still opening upward. And these are higher here, but opening downward, if you had x equal constants.
And you can figure, because if you look at putting legs down, it's coming around this way.
Yeah. And how in the world you get your pictures to show you that without, I mean, anytime you try to project 3 dimensions into 2, I run into problems seeing them.
Well, to tell you the truth, I'll tell you now, I have a lot of problems with this.
What's that?
I have a lot of problems with this.
Yeah.
I just have to go back and just try to read.
Right. Yeah. And if I had to depend on my drawings, I'd have even more problems, you know, for sure. So, we see that one, you might say, application of a gradient, it makes determining your directional derivative an easier thing to do, okay? Because before you had to well, where was it? They really didn't give us a formula per se. You just had to do a lot of head scratching with it. But now that you have the gradient, it makes it a real easy thing to calculate. Well, is that the only good for a gradient? Well, not really. Here's another application of a gradient. Oh, they jump right out with the theorem. All right. They say at the top, you've already seen that there are many directional derivatives at the point xy on the surface. In many applications, you may want to know in which direction to move so that f of xy increases the most rapidly or decreases the most rapidly. This definition is called the direction of the steepest ascent and is given by the gradient stated in this theorem. Okay? If f is a differentiable function at that point xy, then, and if the gradient at f at there is equal to 0, then the directional derivative at f of xy at that point, where the gradient is 0, is 0 for all u. Now, all unit vectors, no matter which way you go, your gradient is going to be 0. Okay. The direction of maximum increase in f is given by del f of xy. That maximum value of the directional derivative along u is then now they say maximum value. That just means the magnitude of alpha of xy. And they say that magnitude is the maximum value. These symbols still mean magnitude. They don't mean maximum value. This happens to be the direction of the minimum increase in f, or the maximum decrease in f would be the other way to look, would be minus that, going in the opposite direction. If your maximum increase is this way, maximum decrease is that way. And this will be a negative value, okay? Where that is 0, though, if that's 0, then the directional derivative is 0 no matter what direction you take it.
Well, what is the use of if you were on the mountain and you
Right.
had all cross, we don't care
Yeah.
which way we're going to walk, we don't care.
Right.
Now this other thing about the maximum now, we want to stay away from that sucker.
Right. I would anyway, yeah. If you're big on climbing mountains, that may be the direction you want to go, but not me. Okay. That commercial with that guy going up the face.
No equipment.
Not for me. Not for me. That makes my fingers hurt watching him do that, you know. So, but this just gives you the direction of maximum ascent. Is basically what the term they use for that. And then the opposite of that would be direction of minimum ascent. But if
I'm just trying to make some sense. There's got to be something in between
right.
all of this, because just going down to some maximum descent and nothing's down there.
Right.
I don't know.
Well, no, at that point.
Yeah.
At this point, x, y, this would be direction of maximum ascent, minimum descent, and the directions this way and that way would be on the contour.
Oh.
And then in between, you'd be flat here, going up to maximum ascent, going down this way, you know, same thing. So,
this got to do with level and contour curves.
right, exactly. That's what it's talking about. This gives you maximum ascent, and where that's equal to zero vector, you're on the contour. Okay. You're not going up or down. So let's see. To me, it's not a great one to start off with, but it is one. The temperature in degrees Celsius on the surface of a metal plate. Okay, you got a metal plate, assume it's a flat metal plate. The temperature is any point x, y on that plate. Now, obviously, after looking at this, when x equals 0, y is equal to 0, then the temperature is going to be 20 degrees, which is room temperature, degrees Celsius, okay? And any other place on this plate is something less than that, because then you're going to be subtracting something from it, more or less something from it. So, where x and y are measured in centimeters, so whichever direction you go, the maximum temperature is at 0, 0, and then going out from there, well, you can see sort of where you're going. If you move these, okay, well, like that. In what direction from to -3? So when x equal 2, y is equal to -2, does the temperature increase most rapidly? I can almost tell you it's the thing going toward the origin. Okay.
Y is square.
Yeah.
Because you got 3 is going to be square, and the 2 is, it's got to go up.
Yeah, it's got to go up. So in what direction from that point does the temperature increase most rapidly? So what we're going to do is take the gradient at that point. So del or grad of t of xy is equal to
8
-8
xi,
I,
then 2 minus 2yi, j.
2yj. Perfect. Now we want that. In what direction from that does the temperature increase most rapidly? Okay, well, let's plug in the point. So we want the del, the gradient, t of 2, -3. This will be minus 16i
and
plus 6j.
6j.
Okay. So let's let this board right here be our plate. Okay, I think that will work okay. And the temperature, let's see, out of the board will be positive. So out here at 20, whatever that is, that's going to be your maximum temperature. Okay? If you're at 2 -3, 2 here, -3 there. Okay? So process of doing that, this would have been minus 16 minus 9, so that would have been minus 25 euros. So you're at minus 5 degrees Celsius. So somewhere back there, behind the board, okay, that's your temperature now. Whereas the maximum rate of increase, you're saying it's in the minus 16 I direction plus 6J direction. So you would have to be heading back toward the origin here, and well, in a positive, yeah, because you're down here. Here's your maximum, so you'd have to be going negative in X and positive in Y to get toward that maximum temperature, and that's exactly what we got now. I'm a little surprised it's that big a number on the I, but that's what it tells us it is. Okay. And that at least sort of makes me feel warm and fuzzy there, because remember, yeah, you're way behind the board there.
That's the question I have right here.
That's what?
The question I have is like,
yeah.
Went down to 2 minus 3.
Yeah, 2 minus 3.
Okay. Now, this says you all the way in the back of the board.
Yeah, this is the point, but you're behind the board 5 units.
Okay.
Wasn't it?
6 units.
6 units, okay, whatever it was. Maybe that was then minus 16, so that gets you down to 4, and then another minus 9. That'd be minus 5 units, wouldn't it? Minus 5 degrees right there. Minus 25 here. 9 and 16. So minus 5 units back there somewhere. 5 units into there. We're 20 units out here is the maximum temperature. So you'd have to be where? Yeah.
Where's the vector going now?
Yeah, the vector is going from that place back there toward this place here. So you see that vector has a negative component on X and a slightly positive component on Y.
Okay, so this is almost like the Pythagoras theorem. You get to cross over.
Yeah.
To get out here at 20.
Right, exactly. To get out here to plus 20. And I'm just surprised it's that big. But I guess it's because, yeah, you have a large coefficient there, and yeah. So anyway, I sure hope that's right, because that's what I've been saying it is. That would be minus 16I plus 6J. In what direction from to negative 3 does the temperature increase most rapidly? What is this rate of increase? Okay, so that's the directional gradient, isn't it? Oh, goodness. That was a terrible burp. So, no, it's just the magnitude of that. Okay. So, this is the direction of increase. The rate of increase would be the magnitude of your gradient vector at 2, negative 3. And that would, ooh, goodness, that's going to be a huge thing, isn't it? 16 squared, which is 256, plus 36 is the square root of 292. Square root of 292 is going to be something in excess of
in excess of 16.
Yeah, something in excess of 16. They said 17.09 degrees per centimeter. Okay. Now, I'm trying to come up with a rationale of how they got the units. I know your delta T on top, that would give you your degrees, and then the total area underneath, or the direction underneath would be in centimeters. So, but there's nothing about this problem that makes that clear to me, that would be in degrees per centimeter. Obviously, changes this, and since this is partial of T with respect to X, partial T with respect to X, yeah, that makes sense. Degrees per centimeter. Yeah, that makes sense. Okay. The rate of increase would be the magnitude of that. That would be the direction of increase. That would be the rate of increase. And if it's going from -5 to +20, that's a 25-degree change over the length of, that would be square root of 13 here, so yeah, that. I think, yeah, seems like it makes a certain degree of sense anyway. Okay. All right, 17.09 centimeters now.
You still asked us what direction.
No, the direction is this.
It's coming out to 20. Okay.
Yeah. Here is the direction, and this is the magnitude of that direction.
Still confused this board with X and Y. So
What's that?
I'm still confused this board with X and Y.
Right, exactly.
I can't get behind the board.
Yeah, exactly. It's somewhere back there pointing this way, and it's pointing negative on X and positive on Y, because that's where it is back there, to get up to something over the origin out here at 20 units. Direction of maximum increase. Yeah. And the rate of increase is the magnitude of the gradient vector. Just taking their thing. So let's see. I've got to erase. All right, so the gradient vector, just like we did, was minus 8xi minus 2yj. And then at the point 2, -3, that would be minus 16i plus 6j, okay? And that the rate of increase is the magnitude of that, which is square root of 292. Now, does this help me see it any better? I'm not sure. These are contour circles or contour ellipses. This is the xy plane, so 2, -3 would be, I guess, right about there. I wish there's a tick mark. Oh, I guess these are on tick marks. There's 1, 2, and 3, yeah. 1, 2, and 3, that's why you can't see them. I can see these better. This is -1, -2, -3. 2, -3 would be here. Okay. Now they haven't listed what the temperatures are. This one in the center is at 20 degrees. And then the next one at 1, 1. No, this is 1, 1/2.
How could it be if that's an ellipse? Because both the corners, well,
Right. Okay. Let's.
everything's a square, and then it's
Right.
but the denominators are different from AA or BB.
Okay. Let's just take this first circle here. That's the level curve when x is equal to 1/2 and y is equal to 1. Okay? So you'd have t at 1/2 1 is equal to 20 minus 1/2 squared would be 1/4 times 4 would be minus 1, so this would be 18. Okay? So this is your contour at 18. At the center is 20, 18. I'm guessing this will be 16. No. No, it won't go down by, no, sorry, that's not right. 18 would be, ooh, that got worse, didn't it? Okay. You'd have to plug in the next one, which would be at x equal 1, y is equal to 2. Okay. So t at 1, 2 would be 20 minus 4 minus 4. So this would be 12. So that's 18. This is 12. The next one would be t at 3/2 3. And that would be 20 minus 12 minus 9. So this would be -1. So this would be -1 contour. This doesn't seem like it's going right. Let's do the next one. Yeah, okay. Next one would be t at 2, 4. No. Yeah. I think so, if I'm doing it right. This would be these are the temperatures at, I'm not quite doing this right. This is not that level curve, sorry. This is the point at, this one would be 1/2 1. That would be right here. You'd have to get, okay, let me go back and do these correctly. Okay. Let's pick the easy one to do, the Y's, because those are on the thing. Okay. Sorry. This one at x0, y1. That would be at 0, 1. This would be 19. Okay. So this is contour 19. T at 0, 2, that would be 20 minus 4 is 16. And t at 0, 3, that would be 11, right? And t at 0, 4 would be 4, and t at 0, 5, which is where we are, is at minus 5. It's minus 5 up here, minus 5 here, minus 5 there, because that's, you know, everywhere on that contour is minus 5. So that's where we are now. And the direction of maximum increase in temperature starts off being there. Now this is a tricky part. This has to be, we're going to get to it in a minute, a right angle there. If it got us to this point, then it's going to shift a little bit, because these aren't circles, these are ellipses, and every time it's shifting a little more until finally here. So your actual thing of maximum ascent would be something like that. Everywhere you cross a contour, you have to be at 90 degrees. And 2 degrees or something. Now that's coming up later. I'm just telling you that now. It doesn't mean this is going here, so the maximum is going to be somewhere out here somewhere. Every time you approach a contour, you're twisting to always be perpendicular to that. That's a little ahead of where we are now, but that's why it looks like that's not going to the point of maximum thing, because in fact, it's not, you don't get to a contour, there's infinite number of contours there. Every one of them bends you a little bit until you're pointing toward the sun. So that would be your path of steepest increase. But that's where you get started on that line, is going perpendicular to it. Whereas the gradient here is 0. So to move along here, you're not changing temperature at all. You go in this direction, you're the maximum decrease of temperature. And again, that would probably bend this way. Maybe bend, however, I don't know. Has to have an asymptote or something down there somewhere. Yeah, but that would be those would be the contours you actually were following. All right. I think we beat that to death, didn't we? Okay. Maximum of that. The rate of increase would be the magnitude of your gradient. Okay. Now, this is sort of getting to what I was saying. The theorem, whoa. They skipped example 6, so let's go back. Ooh, not a lot of room to write. Not a lot of room to write there either. That's right. Well, there's a little more room to write here. So let's do example 6. A heat-seeking particle, or think, what is the name of that rocket? Stinger? I can't remember which one it was. It actually is a heat-seeking anti-airfare.
I know the one that all the pilots they hit the sun.
Oh, that's right. I hadn't thought of that. Yeah. And then when it gets close, try to divert in a hurry and get it to follow the sun. I see. I hadn't thought of that. Finding the path of a heat-seeking particle. A heat-seeking particle is located at the point 2, -3. That's pretty convenient, isn't it? On a metal plate whose temperature is that thing we were just doing. Why did I erase all that? Find the path of the particle as it continuously moves in the direction of maximum increase. Yeah. Okay. So the path is represented by the position vector r of t is equal to some x of t in the I direction plus some y of t in the j direction. Okay. Let's see. All right, we got plenty of time. I was beginning to think we were getting short of time, but we got plenty, I think. Okay. Tangent vector at each point x of t, y of t is given by, now you might ask yourself, why a tangent point? Well, that's going to be along the contour, so that's going to be 0 increase. That would be x prime of t I plus y prime of t j. Okay, but they gave us, let me write it down, t of xy is equal to 20 minus 4x squared minus y squared. Okay? All right. We don't need that yet, but I was just going to do it. Now, so what we have here, your gradient of t, or del t of xy, like we did before and I erased it like an idiot, is minus 8xi minus 2yj. Okay? Now, because of that, that says that at every point xy, this has to be, that has to be derivative of this. So this is saying that x prime of t is equal to minus 8x. Okay? Now, your primes is with respect to t, not with respect to x. Okay? So they also put a k here because it's within some constant of that. You know, it doesn't have to be constant of 1. And minus 2y is equal to minus, I've got them backwards here, minus ky prime as a function of t. And the prime indicates the time rate of change. Okay. Now, and perhaps I should have written it that way to make it clearer. I was just being lazy because I don't like to write so much, but this is dx dt, and this is dy dt. Okay. My nose is itching. Now, if this was our other class, differential equations, it would be okay because we would just say separate the variables and go. And they do that. Shame on them. They could write this as dx over 8 is equal to minus kt dt. That's not right. One over k dt. I left off my x. Okay.
Why couldn't you do dx over x is equal to 8 kt?
Yeah, okay, yeah, that's, well, not kt, 1 over kt, 8 over kt. You could do it that way. It's perfectly fine. In fact, that may be a better way to do it. And then this would be that's a plus there. I don't know how I got a minus there. Oh, I wrote them backwards. Okay, So this would be a dy over y is equal to 2 over k dt. Okay. Minus 2 over k dt. Oh my goodness gracious, I'm stiff. I didn't do that much this weekend, but I feel sore all over. Because the k's are the same, they relate, and I guess the dt's too. Seems like they really are. By solving for dt over k, that just doesn't even seem right. Okay, so what they did was go back, rather than what you suggested, which I went along with because it made sense to me. They put the dx over minus 8 here is equal to k dt, and dy over y is equal to minus, oh, they put the 2y here, minus 1 over k dt. Okay. And because dt over, it's not a minus, I don't know why I keep wanting to put a minus in there. Okay. Because these are equal to each other, then they say there is a minus there. Dx over minus 8x is equal to dy over minus 2y. Seems like they're running around in circles almost here. And then they just throw out what the solution is, which has to drive you nuts, okay, because they don't tell you how they get it. We know kind of how they had to go about getting it. But partly is you can multiply both sides by minus 1 and you get rid of that, and then you get multiply both sides by 8 and you get a 0 there and a 4 here, okay, and they just say, and lo and behold, the solution is x is equal to c times y to the 4th. And that is true, but you have to have differential equations to do that. And to do that, that'd be log x is equal to 4 times the log of y. And then e both sides, you get x is equal to, make this y to the 4th. Now e both sides, and you get y to the 4th. Okay, and you could say plus some c, but make it a log c, that constant a log c, and that makes it c. But how incredibly awkward of them to do that to you. You don't have any, we don't have any basis of differential equations here. There was a chapter on it, and maybe that's enough, but we skipped that chapter because it's that's another course. And because that point, the particle starts at the point 2, -3, you can go back and say, when x is equal to 2 is equal to c times -3 to the fourth, it's going to be c times 81. So c is equal to 2 over 81. And that's what they got in the book too. Without really showing you how they got it, but that's what they got. So the path of a heat-seeking particle would then be x is equal to 2/81 times just had it. I can't see. There it is. Okay. 2/81 y to the fourth. Okay. And that's when they show in the text what I was trying to show figuratively on the other drawing. Here's that curved thing. See, the direction is just like this direction here, but then it's curving up. And if I'd have been thinking about it, I would have known it had to be pretty close up to y-axis here, because that's the perpendicular to this, and that heads you straight up there. So there's the curve represented by that. X is equal to 2/81 y to the fourth. Of course, that's written that way. There's your y to the fourth, x equal y to the fourth curve like that. Or the mirror image of it. Okay. Wow. Okay. And they say in that figure, the particle determined by the gradient at each point appears to be orthogonal to each of the level curves. And sure enough, that one you could almost draw your 90-degree angles there, and you would, it looks like that's right on the money being that. Now, the temperature along a given level curve then has to be 0, because you're going not in the direction of maximum increase or minimum increase, but if you're going along the curve, you're on the contour. So your change of y would be 0. So that's what leads to there was my poor drawing of it. Let's try to do a little bit better job of that. Okay. So it's perpendicular there, 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 and there. So it does come up about like that. A lot better than what I did. Okay. So here is the theorem that's top of page 926. The gradient is normal to the level curves. The gradient is always perpendicular to that level curve at every point on the curve. If f is differentiable at x0, y0, that has to be true. Then del f, or the gradient of f at x0, y0, is not the zero vector. Okay, and this is the other condition. Because if it's a zero vector, that means there is no direction of maximum increase. Okay, then the gradient f at x0, y0, if it's not equal to 0, is normal to the curve through the point x0, y0. That's basically what we're just saying. If you're going along the contour, you are perpendicular to the direction of maximum increase or decrease.
I know it's got to be normal. I'm trying to see the picture.
Right.
And I'm going around this way.
Yeah.
So you're saying, well, normal, if it's going this way, normal would be going the opposite way.
Okay, yeah, okay. If you're going along the contour like this is a way where you're not changing elevation at all, then immediately to your left, if that's a high point there, that's in the direction of maximum increase, that's the direction of maximum decrease. From that point right there, because you're zero this way, maximum increase there, and it goes down. Now, doesn't quite seem to me that it would necessarily be that way if the thing was going up at a real rapid rate here and then smoothing off here. It seemed like maximum increase could be something different. But I think that then the F being differentiable sort of takes that into account. I can't say why I think that, but that's what it feels like on a gut level to me. So here's example 7. Finding a normal vector to a level curve. Since the level curve corresponding to C equals 0 for the function given by, see, there's no C anywhere in here. It says sketch the level curve corresponding to C equals 0 for a function given by f of x equal y minus sine x, and find a normal vector at several points on the curve. Okay. Okay. All right. Just being in this chapter, I would think one of the first things you got to do is take a gradient. Okay. Sketch the level curve corresponding to C is equal to 0 for the function given by that. Okay. Now what they say this means is F has to be 0 there. If that's a level curve, then, and they don't really give you a very good reason for this, but they say the level curve for C equals 0 is given by this thing equals 0 is equal to y minus sine x. Okay, I got what they mean now. Remember what the C is, okay. C was equal to f of x, y. Remember, that's what they talked about. The C is equal to f of x, y. And when C is equal to 0, that of course. Okay, that's what they're meaning. Okay, I was trying to read too much into it. Now, what that means is that y is equal to sine x. Okay? So your sketch the level curve corresponding to that. Well, here's what it would be. It would be a sine curve, where this is your y and this is your x, and this would be pi halves, pi. Writing faster than I'm thinking, which is not very fast necessarily. And this is 3 halves pi. This is 2 pi. And so on. Okay? Now, sketch the level curve corresponding to that, you need this in the z direction. So take this thing, flatten it out, and then do a sheet metal curve like that. That would then be coming out of the board, this plane that does like this. That would be your level curve. Okay? It's a cylinder, but not a closed cylinder. Okay. Because the gradient of f, and this is where I knew we would ultimately get to this, the gradient of f of xy would be what?
1 minus plus cosine of x.
Okay, I didn't understand the 1 minus. Isn't it just minus cosine x?
That's right, because I'm just doing
I. See, when you take the partial of this thing, going back to this thing now, this f.
that was my mistake.
Yeah, okay. And then it would be plus j. That's the gradient. Now, I haven't told you why you're doing that, but that's the gradient. Okay? Oh, well, it's by what they were doing before. That gradient has to be perpendicular to the curve at every point. Okay? And
if it's the opposite, can't we just say minus j plus cosine I?
yeah,
Would that make it normal?
okay, let me think. You're probably right. Okay. I haven't quite figured out why they started here, except it's just some place to start. They say the gradient of f at negative pi 0. Okay? Negative pi would be the x value. And cosine at negative pi, cosine at negative pi, let me put this in a different color. What color you want cosine to be? Pick a color.
Negative pi?
Yeah, pick a color for cosine.
Oh, red, I guess.
Red, okay. Danger, okay. Your cosine is this then. Okay. Okay, something like that. Okay. Your gradient is then that. So, whoa, I hit the wrong stupid thing. Okay. Trying to get back to black or dark here anyway. Okay. So, the gradient of minus pi, this is minus pi halves minus pi, that's going to be a minus 1. That'll be a minus I. No, it's minus a minus I, so it'd be plus I plus j. Because, no, it's 0, isn't it? Seems like that'd be a 0. Just plus I, but they put in the book Oh, when y is 0, but you see, yuck, this is 1. Okay, it's j. Okay, it doesn't matter what the y is. There's no y in that, so that's just j. So it's I equals j. They have that right. Okay. I still haven't quite figured out why they're doing it yet. They pick another point, and for the life of me, I haven't quite seen why. Del F at negative 2/3 pi minus square root of 3/2. Just sort of picking points kind of randomly, it seems like. Maybe not. Let's see, maybe they're choosing that from here. When x is equal to minus pi, your y then would have to be, now we're on the sine curve, it would be a minus 1. But the gradient doesn't care what y is, it would be 1 cosine of minus pi would be 1. So I think I see what they did. Just pick an x. They chose minus pi. This tells you your y is 0. This tells you the x value is 1. The I value is 1 because, and then this tells you the j value is 1. Okay, so pick a different x equals minus 2/3 pi. This tells you the y is
1. Is that 1?
No, when sine of negative 2/3 pi. Here's negative pi has 2/3 pi would be over here. That would be 1/2, I think. Negative 1/2. So it would be negative 3/2. Obviously, I did it wrong. 2/3 pi, yeah, would be up there. I'm sorry, I did 5/6 pi. 2/3 pi would be here. That would be negative square root of 3/2. So choosing an x here gave you this. Calculating it here gives you this. Okay? Then putting, because the gradient of alpha at this point then would be minus cosine of minus 2/3 pi, which would be negative 1/2. So that would be your I term, negative 1/2 I. Okay, and then plus j, because it doesn't matter what the y value is. So they got positive 1/2. Oh yeah, because it's a negative cosine. Cosine's negative 1/2. So, and negative of that would be plus. Goodness gracious, this is so convoluted. Okay, so according to what they're doing, they'll do the next one. It would be let x, let me write it down this way. Let x equal minus, why did they jump to minus pi halves? I don't know. Minus pi halves. Okay. That implies that y is equal to, okay, sine of minus pi halves is 0, so y is equal to 0. Okay? Then that tells you that the gradient of f at minus pi halves 0 would be cosine of minus, I went to the wrong curve, didn't I? This is driving me nuts. Okay. If x is this, okay, let's get on the right curve. When x is minus 1/2, y is minus 1. Okay, down here. And the gradient is minus cosine of x, which would be minus this, that would be 0, and this still is 1. Okay. Wait, I just put the wrong things in the wrong places. Yuck. Okay. Okay. Gradient of minus pi halves minus 1 would then be, and that's where I should have put j. Okay. Let's see if that one came out right. Yeah, that came out j. All right. Goodness gracious. Now, they've done minus pi, oh, okay, they started here and went to here and went to there, okay? And then the next one I guess they'll go to is minus pi thirds, okay? Minus pi thirds would be here, okay? So let x equal minus pi thirds. That would imply y is equal, go up here, x minus pi thirds, y is going to be minus root 3 over 2. Right. Then the gradient of f at this x value minus pi thirds minus root 3 over 2 is going to be minus cosine of this. The cosine of that is going to be a positive 1/2. So 1/2 I plus j. It doesn't matter what the y value is. So that's minus 1/2. Yeah, minus 1/2 I plus j. I said, okay, I keep forgetting, it's minus cosine, and that is a 1/2 value minus that would be minus 1/2 plus j. Whew, goodness gracious. The next one, so you see they started at minus pi, minus 2/3 pi, minus pi halves, minus pi thirds, and then they are going to 0. So let x equal 0, then y is equal to 0, then the gradient, that's a pretty ugly gradient, that's getting worse. Oh, we're almost out of time. Okay. The gradient of f at 0, 0 is going to be minus cosine. So when cosine is 0, when x is 0, cosine is 1. So this will be a minus I plus j. Yes. Okay. I got what they're doing now. It sure is a pain in the neck. And they continue like that. And I don't know why they listed all those. They didn't say that. They said, and find a normal vector at several points on the curve. So these are your normal vectors, which are the gradient of f at those values on the curve. Okay. And then they drew them in. They drew this one to be plus 1 plus j. So that was here. Normal there, it'd be, yeah, that's exactly right. Plus I plus j. You're right like that, okay? Down here, this would be 1/2 I. Very gentle slope there, but you know, good distance on j. And sure enough, that's what it looks like. And then at negative pi, negative 1, that's here, your normal vector is plus j, just so.
Well, it looks like it's j at every point.
Say again?
Looks like it's j at every point.
No, I mean, here the normal is like this. Here the normal is like that, like this. Here it's, now, I don't quite see that one.
Well, I can see that one because that's coming right at me.
Yeah. But this one over here is like this. That would be at 0, 0 is one we just did. Minus I plus j. Yeah. So that would be that. So your normal vectors would be here, 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 here. So they're always pointing above the curve, that's in the positive direction, but perpendicular to the curve. So they're little spikies that go like this, always perpendicular to the curve. And that's what this is showing. Man, it was a pain in the neck to get there. All right, we'll start next time. Whoa. Let's see how they did it, okay? All right. The level curve for C is equal to 0 is y is equal to that, which implies that y is equal to sine x. So using those values, the gradient of f is minus cosine x plus j. Then conclude that the del f, or gradient of f, is normal at each point. So you got your minus pi 0 from that first one that was on the previous page. Y is equal to sine x. Okay, so when sine is pi or negative pi, y is 0, and that gave you that point. Y is negative 2/3. The sine of that is negative root 3 over 2. And then when you plug that into your gradient vector up here, this into here, this one, the j is always j. And you're right there. J is always here, but you have different x's that go with the j's that make it tilt in different directions. So this one, depending on what that cosine is. So the first one there is ij, like this, where it crosses the x-axis minus pi 0, and then they sweep around like this, but always the j is always 1 up and the X's keep it going back and forth like a metronome. Okay, only they're changing lengths as well. Metronomes don't do that. Okay, so they list several of the points. Now, getting those points is a pain in the neck because you go back to the y is equal to sine x to get those points, and then you plug that into the minus cosine xi plus j. So the plus j is always there, but your something about one of those that makes me suspicious they have a sign wrong. No, that's right. Okay. Yeah. Okay. And then this is the curve. What I was getting suspicious at was these two. These two, those two, both being in the same direction. That's because you're here, here, here. These two are in the same direction. Okay. And then this one and the one down here will be in the same direction if we have gone that far. And this one, and the next one here will be in the same direction. Okay, so that does do okay. All right, we'll start next time with functions of three variables. Actually, start one half step sooner than we did last time. Okay. All right, good deal. Sorry. Homework exercises here. Let me get something to mark my place. Oh, we almost finished. You can do either 3 or 5. They're both at Calc Chat. 3's at Calc View. 7 or 9, both at Calc Chat. 7's at Calc View. 11 or 13, both at Calc Chat. 15 or 17, both at Calc Chat. 17's at, any of the odds 15 to 19. 17's at Calc. They're at Calc Chat. 17's at Calc View. 21 or 23, both at Calc Chat. 25 or 27, both at Calc Chat, but 25's at Calc View. 29 through 37, all at Calc Chat. 31's at Calc View. 39 or 41, both at Calc Chat. 41's at Calc View. 43 or 45, both at Calc Chat. 47's at Calc Chat. 49's at Calc Chat. You can think about doing 51 if you'd like. It should be at Calc Chat. 53's at Calc Chat. 55 should be at Calc Chat. 57 should be at Calc Chat and Calc View. So should 59. 61 and 63 are both at Calc Chat, or should be. 65 should be at Calc Chat. 67, they don't have any with 3 variables that I saw. So I didn't, maybe I missed some. If you find any with 3 variables, wait on it until we get that covered. But I didn't see any that had 3 variables, 3 independent variables. All right, and we'll pick up there next time.